Welcome to RISE Learning Machines seminars. RISE is Sweden's research institute with 3,000 people working on topics spanning from bioeconomy to digital systems. Specifically, we at the computer science department work on applied AI projects, and we organize these seminars every week, Thursdays at 3. This meeting will be recorded, and if anyone wants to be removed from this recording, just let us know. Also, make sure to check out the collection of great talks on our YouTube channel. Today, I have the pleasure to introduce William Lidberg, who is an assistant professor at Swedish University of Agricultural Sciences. He's leading an interdisciplinary research group that combines soil science, hydrology, remote sensing, archaeology, and AI with social science to solve problems in forest management. Today's topic is geographical intelligence. And with that said, I will hand over the word to you, William.
Thank you. I just need to switch slide first. Hold on. There we go. Thank you. I work at the Swedish University of Agricultural Sciences. I'm located in Umeå. So right now it's really snowy and dark outside. And the term geographical intelligence is a combination of geographical data and artificial intelligence. I thought I was really clever when I came up with it, but then I Googled and noticed that I wasn't the first one. But what I'm going to talk about today is a few examples of what my research group and I are working on right now, or have been working on. First, I'm just going to give a brief introduction to the geography of Sweden, talk a bit about forestry and then specifically Swedish forestry, some LiDAR, and the traditional topographical way to model water. And then I will briefly go through the AI methods that I have been using. My background is in soil science, so you will have to take these explanations with a grain of salt. Then I'll talk about the implementations, how we use AI to detect soil moisture, soil types, ditches, and cultural remains. And then finally, I will talk a bit about whether this is a good idea or not. So first, we'll have to start with the geography of Sweden. I'm not sure if you're all aware, but most of Sweden is actually forest and wetlands, especially the northern half of Sweden. So the majority of our land use is just forestry. And if you look at the population density of Sweden as well, most of people in Sweden live in the southern half. So 90% of everyone living in Sweden live within this circle. And just about 10% live in northern Sweden. And then mostly along the coast as well. This is another way to represent the distribution of people in Sweden. And you can see that the northern counties have quite small population compared to the southern half. And then this is a cool map of the redistribution of people since I was born, so back in the 1980s. Essentially, people have been moving from the green areas to the purple areas. And this is a trend that has been going on for quite a while now, and it's still continuing. And this has some implications for forestry as well. The forestry in Sweden is quite intense. We have big machines. Some of the biggest ones in the world are in Sweden. That's because they're the most efficient ones. So you can say that only a handful of people are managing most of Sweden's land, at least the terrestrial area. And about 60% of all this land is owned by males as well. So, and the majority is owned by females. To do this with such a small workforce, we have used a lot of automation and digital tools, and it's quite efficient. But it's not without problems. So I'm going to discuss a few of the water quality issues in Swedish forest first. And I have this cool graph. The rings will represent the scale. So the inner ring is local, then landscape and national scale. And the colors is going to represent how severe the problem is. So for example, the red areas are issues on water quality caused by sediment and mercury. And those are quite severe on both a local and regional scale. And we also have issues with nitrogen and phosphorus, for example, which are fertilizers, organic matter, and runoff, and dissolved organic carbon as well. So these are like the major quality issues in Swedish forests. This is a similar graph in grayscale this time. The black areas represent the problems or issues where forestry is the primary cause. So you can see there that sediment and mercury is quite severely caused by forestry. And the reason for this is mostly related to rutting or damage to forest soils caused by heavy machines. If you try to drive a 30 or 60 ton machine across a wet area, it will damage that area. And this damage both compact the soil, you get decreased forest production, we change the hydrology, so the streams might take a new course. We also get erosion of sedimentation in nearby streams. Those sedimentations kill plants and animals and destroy habitats. And we also get leakage of nutrients, and this will hinder our environmental targets as well. So this is something we want to avoid. I'm just going to bring up mercury as an example. The deposition of mercury is not caused by forestry. It's caused by burning fossil fuels. But the mercury is now in the ground, and if we damage the ground, this mercury will start to leak out into the water. So about 15% of all the mercury in Swedish fish is related to Swedish forestry. And as an effect of this, pregnant women are not recommended to eat fish from Swedish lakes, and not kids either, at least not more than like 2 or 3 times a year. So again, most of Sweden's land is owned by men, but the effects are mostly for females. But the main reason for this is because we don't really know where things are. The traditional way to draw a map is to use aerial photos. And from an aerial photo, you can't really see what's beneath the forest. And since most of Sweden is covered by forest, we have very little idea on what's actually underneath that forest. So around 80% of all the streams are missing from the best maps we have of Sweden today. 64% of all the wet areas are missing, and parts of northern Sweden don't even have a soil map. And if you try to plan forestry operations under these conditions, you can't really plan on where to drive your heavy machine if you don't know where the wet areas are or where the streams are. And once you reach a wet area, it might be too late to turn around. But the solution to this problem is LiDAR. It's light detection and ranging. And what we do is, well, not we, but the Swedish Mapping and Land Use Agency, together with the Swedish Forest Agency, have mapped all of Sweden using LiDAR. So they fly with an aircraft about 3 kilometers above the surface, shoot laser pulses down towards the ground, and then count the time it takes for the laser to bounce back to the aircraft. And the pulses that came back to the aircraft last are the ground. Those pulses have probably hit the ground. So this is an example of how these point clouds can look. So on the left, those 2 points are actually our horses, which show up in the LiDAR data. And on the right, you have a small forest section just draped atop the current topographical map. So with this technique, we can go from having no information about the soils or the landscape to having a very detailed information about the landscape. So there are, Sweden has been scanned once with the density of like 0.5 point to 1 point per square meter. A second scan is underway with twice the amounts of points per square meter, and a third scan is being planned with even more points per square meter. So the density of these LiDAR clouds is continuously improving as well. And I will start to talk about the first scan. The resolution of this data is 2 by 2 meters. And I live in Umeå, And sometimes I have to go down to Uppsala by train. And then I usually sit and look out the window for quite a few hours. So, and then I try to imagine how many of these 2 by 2 meter pixels or squares, how many of them like fit in a grid across the landscape outside the train window. And it's a lot of data, around 1.4 terabyte of data in total. So, but with this data, the first thing I want to try to do is traditional topographical modeling. It's when you take the digital elevation model, you pour water on it in the computer and just calculate where the water is going, which direction. And when enough water has accumulated in the same area, it goes from being groundwater to being surface water, and as a form of a stream. One of the issues with this though is that we have roads in the digital elevation model. It's so detailed, so we capture roads and bridges as well. And if you try to pour water on the model, these roads will act like dams and just stop the water. So what we want to do is to make a trench across all the roads in Sweden. So this is what I did for during my PhD. These are just a quick example. This is the original digital elevation model. You can see a stream channel and then a road in the bottom right corner. If you use the traditional methods, you will just fill up that area and lose a lot of the information. But if you breach it instead, just burn a channel across the road, you will retain the information above the road, but you will also end up with a much more accurate stream network. So with this knowledge, I started to implement the traditional topographical models on all of Sweden. And with this approach, we could map most of Sweden's stream, and we could follow them from the small trickle in the forest all the way out to the Baltic Sea. We could see the entire stream network as a network for the first time. So it was pretty cool. But we can do more. This is normally when you harvest forest, you have to leave a buffer zone around streams. And first you need to know where the stream are in order to leave a buffer zone. But the wet areas around the stream are not the same in all areas. So in this image, for example, you have a stream in the middle, but you can also see that you have some ruts, some tracks next to the stream. So instead of having a fixed width buffer zone, something like this, we suggest that we have more dynamic buffer zone where wet areas get more protection than dry areas. And that's something that's closer to how natural disturbances also have behaved, like forest fires, for example. And to do this, we can start with combining the streams that we extracted before, and we use the terrain surrounding the stream. And if the area next to the stream is a flat area, it's more likely to be wet. And if the section next to the stream is dry, it's more likely, if the slope is steep, it's more likely to be dry there. And by using this approach, we can create a wet area map. It's called Depth to Water and was developed in Canada a few years ago. One of the issues though, is that depending on the season, the streams will start in different areas in the landscape. So during the spring flood, for example, we have a larger stream network than during the summer. So in the summer, the water dries up and we get a more contracted stream network. And we also have different soils across Sweden, different climates. So trying to adjust this wet area map or these streams for all of Sweden is quite difficult, at least with the traditional methods, which I spent 2 years trying to do manually. And then I discovered machine learning, and then suddenly it worked a lot better. But before I go into that, I need to give a brief introduction to the machine learning methods that I have been using in my projects. So I made a quick guide for dummies. Normally, I have a different audience when I talk about machine learning, so you have to bear with me for a bit. The traditional difference between what I was trying to do was to write very specific instructions using traditional methods. But instead of doing that, we can just feed the computer with data instead and let the machine deal with it. So I started out with decision trees. This decision tree is, for example, if you're looking for wet areas, you can ask questions like, okay, is this location next to a stream? Yes or no? And then you go down into the tree and ask another question. Is this area in northern or southern Sweden, and then you go down in the tree and make another question. So this is one decision tree, but then you can have multiple decision trees. One of the most common method is called random forest, which is actually a quite robust and simple method to use. Then you have multiple decision trees randomly generated, and they sit down and vote whether it is going to be wet or dry, depending on the data they have trained on. And if more trees vote for the same thing, it's a higher probability for that class or that outcome. I used a slightly different variation. I used something called extreme gradient boosting instead. And this is an example of how it's working. Instead of building a bunch of random trees at the same time, you're building trees that try to correct for each other. So in this example, we're using the Canadian flag as training data. The first tree will just try to find a big patterns. Okay, there is something white in the middle, something red on the side. And if you add some trees, it will try to correct what was missing in the middle. And if you add even more trees, you get a better picture of what's actually going on. And if you add a lot of trees, you get something that's quite useful actually. So that's the method I will be or have been using. Another way of doing it is to use neural networks, and they're actually quite simple. The name just comes from biological neural networks, and they are sort of similar, but not quite. So you, on the left, you just feed in the data. If you have a table with data points, for example, the arrows are weights that you apply to the data, so you just multiply it. And then you have a hidden layer with neurons that activate if the value of the multiplied weights add up to above that a threshold, for example. And you use an activation function for that. I won't go into that in detail. But if you have more of these hidden layers, it's called a deep neural network. But we are working with maps now, with images. So another approach is to use convolutional neural networks. Then you can decide whether one image is an image of a cat, for example, or a dog, or a number. So you apply a bunch of filters or convolutions to the image. And then these filters get smaller and smaller until you get something that can feed into a fully connected neural network. And then you can train that network and get an output. So this would classify the entire image into something. Okay. Yeah, this is object detection. I used it to monitor horses in the stable. It was quite fun for a bit. But if you don't want to classify the entire image or find an object in an image, you can use segmentation as well to classify each pixel in an image to something. And a unit is unit is also used for self-driving cars, among other methods. So each pixel in the image get a class or classification in the output. And one special thing with machine learning is it can require quite a lot of computational power as well. Luckily, we have had gamers throughout the last 20 years pushing the development of GPUs for these purposes, mostly for processing images, but images are just matrices anyway. So I stole or borrowed some GPUs from my brother during the pandemic because we couldn't buy any. So these are the methods I've been using. Now I will talk about how I apply the methods. So first up, soil moisture. This is the best map we have for Sweden. It's called the Swedish property map. And in the top left, you can see the brown areas are the wetlands, the blue lines are the streams. And the reason why it's so bad is because we used aerial imagery to draw the map. But with LiDAR, we can finally get true topography underneath the forest, and we can apply this depth to water technique, for example. And to upscale this to the entire country, we need to take into account the differences across Sweden. So from SMHI, we got 30 years of runoff data. And you can see that in winter, the bottom left part of Sweden is quite wet, while the northern part is dry because it's frozen. And then the snow melts in northern Sweden, it gets wetter there, drier in the east coast. In summer, the east part of Sweden is drier than the west part, and the autumn you have different patterns. From the Swedish Geological Survey, we have quaternary deposits, soil types. We also have estimated depth to the bedrock from the soil surface. We have elevation above the ocean, of course, the digital elevation model itself. And from that digital elevation model, we extracted multiple different wetness indices, including depth of water on multiple scales and resolutions. We also have all the existing peatlands from different maps in Sweden. We can also extract like micro topography using the digital elevation model, and also macro topography like river valleys and landscape topography, like big stuff. Of course, traditional modeling as well. Topographic wetness index is a common one. And in this case, we used extreme gain boosting, but instead of the flag, we used the natural forest inventory as training data. And I just want to show how it can look when you train the model. So now the model is training, and more trees are correcting the previous mistakes by the different trees. And by the end, we get something that's starting to look like a wet area map. And of course, we put aside about 20% of the field inventory to test and evaluate our results. So this is the SLU soil moisture map. It covers all of Sweden and have a resolution of 2 by 2 meters. So if we compare the accuracy of the traditional map, we used something called kappa. It's a value ranging from 0 to 1, where 0 is more or less no agreement with reality, and 1 is a perfect agreement with reality. So the traditional topographical map have a kappa value of 0.4-ish. The depth of water map had a kappa value of 0.56, which is better. There is a different map created by Metria, which has a kappa value of 0.58. It's also an improvement. And then finally, the SLU soil moisture map has a kappa value of almost 0.7. So it's quite accurate. At least a lot more accurate than what was existing before. Now I'm going to talk a bit about soils, because we noticed something really interesting. First, I'm going to tell you about the problem with the soils in Sweden, or the soil map. This is the coverage of the soil map, or the high quality soil map of Sweden. You can see that parts of northern Sweden don't even have a soil map. It's just missing. But we noticed something interesting when we trained the wet area model. This is a plot showing how important all the variables for the extreme gradient boosting model was. So the ones in the top were more important than the ones in the bottom. And if you look closer on, you don't have to read the labels, but if you look at these in the bottom, these are the soil map, or variables extracted from the soil map. So sediment, till soil, rock, fine sediments. And they had very little importance to the soil wetness model. And this is a bit strange, because either this could be for three reasons. Either the soil map is, the soil map is really bad, so it doesn't contribute anything. It just confuses the model. But we know it's bad, but it's not that bad. Another option is that soil moisture, soil texture doesn't really have an impact on soil moisture, but that's also strange because we have previous publications showing that it does. And the third option, which is a lot more interesting, is that the information about the soils are already captured by different topographical indices. So the model have learned the soil types without needing the soil map. So we started to look into this, and this is a part of northern Sweden, just a valley up north where we have a lot of our field research. And on the right, you can see the terrain is a bit more jagged. That's bedrock sticking out. In the bottom right, that's sediment. And on the top image, you can see they have these rolling hills, which are till soil. So we have a lot of information about what's underneath the surface, just from looking at the shape of the surface. So what we did was to take data from southern part of Sweden when we have good soil maps, and we used that as training data and applied it to other parts of Sweden. So on the left, you have a good soil map from Sweden, like manually made from the Swedish Geological Survey. And on the right, you have the same area, but now predicted with this AI model, this extreme gradient boosting model. So what we can do now is to improve the old general map of Sweden with this new AI model. It's not perfect, but again, it's a lot better than what we had before. And we can also train for things like soil texture, for example, and other soil parameters. So it can be used for both soil moisture and soil types. So now I'm going to go into ditches. This is where it gets more complicated. I'm going to start from the beginning again. The old traditional Swedish map, the topographical map. And you can see that we have, again, too much trees in the way. With LiDAR, we remove the trees. And with the traditional way of modeling water, we could find these stream channels, which I talked about before. But we notice that something is missing. If you look really close, you can see that we have a lot of these small ditches as well. And those can't be modeled with traditional hydrological methods because ditches are normally dug in like really flat areas where you don't really have any topography leading the water away. And that's probably why they have dug ditches there as well, to get the water to move. So they don't really have a catchment area that's useful. So what we did was to first go out and collect training data. We have digitized 1,600 kilometers of ditches across Sweden in these blue areas, and also some in Poland, Latvia, Finland, to get some data from other countries. We applied a filter to the digital elevation model just to get the values from something else than elevation. So we used a high-pass medium filter and created these pairs of chips with the high-pass medium filter and then the labeled ditch channels. We put aside, again, 20% of the data for testing. So this is just some example of the digitized data we had. So the blue lines are natural stream channels. We have ditches on agricultural land. Those are yellow. All the road ditches, of course. We have quite a lot of roads in Sweden. And finally, all the forest ditches on forest land. And it turns out that 70% of all the channels that we digitized are actually ditches and not streams. So humans have really been out there and changed the landscape. And most of these has also been dug with a shovel, so that's a lot of work. And this is where we use the UNet to classify each pixel into being a ditch or not a ditch. This is some results from northern Sweden. The white areas are just where both the reality and the model agrees that this is not a ditch. And the green areas are where the model agrees that this is a ditch. And the red ones are just false positives where the model says a ditch, but it's not. And the blue ones are the opposite. So this model worked quite well, actually. So on the left, this is an area where my father's grandfather dug a ditch almost 100 years ago. And on the right, you have the same area with the ditch detected by this UNet. And I think that's pretty cool. But what's even more cool is I said we have digitized data from other countries as well. So we evaluated the model on these other countries, and it seems to work fairly well regardless on where you are. I mean, a ditch is a ditch regardless of if it's in Poland or Latvia or Finland. We also noticed that the model picked up a lot of false positives, and these false positives are actually natural stream channels, which we didn't digitize this time. And the model was just punished for predicting those as ditches. So we think that, yeah, we also made a web app where you can try it for yourself. But again, we think that the model can be trained to detect both natural channels and ditch channels, and maybe even separate between them. So that's something we're working on now. But this was during the pandemic. And I wanted to take my research to upscale it, but we couldn't find any hardware. So I borrowed my brother's GPU. I took an old computer, which I had built at the start of my PhD, and put it in my basement. And I promised my brother that I would use the GPU carefully and not use it too much. And this is an electric bill from my house during that summer. I think you can start to see where I started to implement this model on Sweden. It takes quite a lot of power to do this. And this is a cool comparison. On the left, you have both maps show stream density, so the number of kilometers of stream per kilometer of area. On the left is the old traditional property map, and on the right you have the ditch density detected by this model. And if you summarize the length of all the detected ditches, you will reach 24 laps around the equator of the Earth. So that's a lot of ditches. And again, most of them dug by hand. So both the soil moisture map and these detected ditches are implemented from all of Sweden, and we handed them over to the Swedish Forest Agency as open data. So all the forest companies and everyone who wants to use them can now download them and use them as they wish. And we also recently hired a PhD student to work on we call it DitchNet version 2. And now we have digitized the natural stream channels as well. And she's working on trying to map them separately. So can we get a model that can detect both natural channels and ditches, and can we separate them? Because if we can, we will have a database of all channels and streams across all of Sweden, and we can start to replace these channels and streams that we have on current maps with these new ditches or these new streams. And we can start to give each and every one of them a plan on how to manage them. And we can also follow the water and do flood modeling, etc. So I think that's really cool. Next up, cultural remains. This is a bit strange, actually. I will start by defining what I mean by cultural remains. These are mostly remains left by our ancestors throughout the forest, like charcoal kilns when you burn wood to make charcoal, tar kilns when you make tar, hunting pits, which can be thousands of years old for hunting animals, cabins, and then a lot of Sami remains as well. And the problem is that about 27% of them are destroyed by forestry or are being destroyed by forestry operations. So we are in a bit of a hurry to protect what's left. These are some example of Sami remains. So this is a fire hearth and a fence, or an old fence. So these remains can be both quite large and really small. And what we have to do first is, of course, to get training data for our models. We have small archives around Sweden where we have these old forest maps, and some of these remains are actually marked on those maps. So we are scanning those and matching them with the LiDAR data to digitize training data. So this is an example of the new LiDAR scan, where we have the resolution of these pixels is 50 by 50 centimeters. And then we can start to pick out these large cultural remains as well. This is a charcoal kiln, all the remains of one. We also have our other archives digitized. They are not perfect, so we have to go through each and every object and match them up with how they look in the LiDAR data. So they are in the correct order. But this is just a series of hunting pits across an area in northern Sweden. And again, here on the left, we have a hunting pit, how it looks now in the forest. And on the right, we have the same hunting pit, but how it looks in the LiDAR data. So this is difficult. I mean, these pits are quite small and shallow, so it's going to be a challenge to detect them. And the method we're using this time is object detection. I wrote YOLO version 5 now, but they're probably out with 6 or 7 by the time I'm finished. But the idea is to use this approach to map these cultural remains as well. Skogsstyrelsen has made a map of charcoal kilns before based on the first LiDAR data, but they only used a hillshade, like one index of the topography. But we can extract more, and if we use the high resolution LiDAR data, we can pick up small features as well. So these are just some examples of different ways to highlight these hunting pits from the high resolution LiDAR data. And I mean, there is no limit on how many different combinations of these topographical indices we can combine. And well, I mean, the limit is the storage space and processing power, but that's another question. But I think if we combine multiple indices, we can get an even more accurate model. And this is some preliminary results as well. The red dots are the training data, and the green circles are the detected remains. And if we apply some simple like GIS methods, we can just, okay, this detection is too big or too small or not run enough to be a charcoal kiln, for example, and then we can filter out a lot of these false positives. So we can have a quite aggressive model and then just filter out the strange noise with normal method, traditional GIS methods. But still, there is a lack of training data, mainly because it's hard to find. It's a lot of work to digitize them. So instead of, or not instead, but to augment this method, I decided to use transfer learning. And that's where you train a model on some on one problem, and then you retrain a model on data from another problem, and you don't need as much data, which is the idea at least. So to do this, for example, for hunting pits, we need a lot of examples of pits in digital elevation models. So I started to think a bit, where can we find a lot of examples of digitized pits? And then I found the moon, which has a lot of pits or impact craters. And fairly recently, NASA went up there and made a good scan of the lunar surface as well back in 2009. So this is an example from that scan they did. This is an impact crater. I mean, the scale is different, but we can just rescale these craters and select them so the number of pixels match with the number of pixels in a hunting pit, for example, and then pre-train the model on this data first. And if you turn this upside down, just multiply the values by -1, you get something that sort of resembles a charcoal kilns as well. So we can use the same data for both problems, just invert it. Now we have a lot of data on the moon. 1.3 million craters have been mapped. Something that we could use this data, so pre-train a model and then use the Swedish data to do the final training before we implement it across Sweden. And then finally, is this a good idea? And then I have to start with this image again. You feed the computer a bunch of data, it learns and can make a fairly accurate model if you're lucky. But if you start to question it, for example, why did you predict a buffer zone here? It can't really tell you the answer. And now we have handed these maps of both streams and wet areas and ditches to the Swedish Forest Agency, and we made it open data, so multiple agencies are using these maps now for decision making. And let's say the Swedish Forest Agency, if you want to harvest the land, you have to tell them that I want to harvest this plot of land. And they can look at these maps and say, no, this area is too wet. You should leave a buffer zone here. And what if the landowners start to question the Swedish Forest Agency, like how did the model predict a wet area here? And then the Swedish Forest Agency can't explain that, but still they're using this method in their governments. And since most of Swedish management, or I mean, most Swedish agencies are built on trust. That's what happened during the pandemic as well, that we didn't have these strict laws. We had recommendations by the authorities. And people mostly follow these recommendations because we have a higher level of trust in our authorities. But if this trust is eroded, it could have a negative impact on the authorities, even though the map itself could be really good. So for that reason, we have a new project where we collaborate with social science to try to find a way to implement this map without causing harm or damage to the trust between the authorities and the people as well. We have just started this, so we have recruited a new PhD student for this project, but we haven't really taken off yet. But this is something we are going to look into. The same problem applies to the cultural remains, for example. If we detect all the big cultural remains, we still have a lot of small remains which aren't detected. And that could be taken as like, okay, this map of cultural remains doesn't show any remain here, so we can just do whatever we want. But in fact, it could harm smaller remains on the cost of the bigger ones. So that's also an issue we need to discuss. So to summarize, we can combine both geographical data with AI to map previously unmapped features like just wet areas, channels, soils, cultural remains, and I'm sure there are plenty of other features we could map if we wanted to. But we need to do it in the right way, otherwise we could also harm the trust between the people and the authorities. And with that, I would like to say thank you, and it's time for questions. I'm going to stop sharing now so we can see each other instead.
Thank you, William. Do we have some questions?
Did we throw everyone out?
There are a few left in the room.
I have a question.
Okay.
When you look at like large, I mean, like a whole country like Sweden, and you use some model to, let's say, segment all the ditches. How is that done roughly? I mean, because I guess you can't take the whole of Sweden and plug it into a convet and then get the whole Sweden back. So I guess you have to do it in pieces somehow.
Yeah, I mean, the model was trained on a certain size of image chips. In our case, it was like 500 by 500 pixels, which is like 250 by 250 meters on this resolution. So the model can't really swallow or predict anything bigger than that. So we have to split Sweden up into smaller pieces, of course. So what we did was to first split Sweden into tiles, and each tile is about 2.5 by 2.5 kilometers. And then we read that tile into memory, and then in memory we split that tile up into these smaller patches which the module could read and predict on. And then after the prediction was run on all of them, we mosaiced these smaller chips together into a big tile again and saved it out to the hard drive. So we looped over all these 2.5 by 2.5 kilometer tiles of Sweden in that manner.
Yeah, thanks.
So you didn't have any overlap when you did this?
We did have an overlap about 50 meters, if I'm not mistaken.
And speaking of tiles, you have quite nice visualizations in your slides. It's like sort of 3D tiles with different heights and so on. What software is that you're using, if I may ask?
Some of them are actually Minecraft.
Cool.
Because that's a good way to show squares and pixels.
Yeah.
The other ones are used in a software called ArcGIS Pro.
Okay. Yeah,
So,
thanks.
So, very interesting talk, William. Enjoyed it a lot. So one question, about ditches. So the Forest Agency is encouraging forest owners to fill in these ditches and to re-wet the land, the forest. So with that, require some changes to your model, or is it possible to handle that in a nice way?
I mean, the model is used for finding and predicting suitable wet areas for this re-wetting. But once you restore a ditch, you won't have a ditch there in reality, but the digital elevation model still have a ditch there. So that's an issue.
No, but you only fill in the ditch in one point, right? And the ditch is still there, basically. But maybe it's covered by water, so you don't see it in the maps after that.
Yeah, water is a bit tricky because it absorbs the LiDAR pulses as well, so you get a gap in the data if you have a water surface. But the long-term goal of re-wetting these wetlands is that they will fill in with sphagnum, these peatland mosses. So after a few years, there shouldn't be water there anymore.
Okay, thanks.
And I just want to say that if you want to collaborate on this, just get in touch, because I'm not an AI expert. I could use some help in that area. I got a question in the chat. The open data is available from both SLU and the Swedish Forest Agency. I think you can Google like SLU soil moisture map and you should find it.
So question from Caroline.
Yeah, hello. Thank you, William. I'm a student at SLU in Alnarp, and I'm studying forest and landscape. And we have a project working with, I actually am doing a project with mills. There's with water mills. And would there be a possibility of what machine or tool would you recommend to use to, because I think there's a lot of mills, hydro mills in Sweden right now that might shut down. And it would be very interesting to see what would happen to the water landscape in Sweden with the potential effect of a lot of water mills actually shutting down.
Yeah, I understand the question, but I don't think the AI is the right answer. I think you need traditional hydrological modeling for that.
Okay.
But get in touch, because I had a friend who made his master's on modeling hydro dams and the effect of closing them down.
Yeah. Okay. Thanks.
I have another question. I was wondering, again, for the ditches, those are, I mean, I guess you can have some physical prior if you want on how they should roughly look. They are sort of curves in the landscape. And I was wondering, in the segmentation approach that you discussed, did you somehow inform the neural network of some of the physical properties? Like it cannot be like a very wide thing, for example, it should be quite thin.
No, we didn't, but it sounds like a good idea. The reason why we didn't is because I didn't know it was possible.
Yeah, I mean, that makes sense. And I was just, yeah, maybe that could be something you can consider in the version 2 or something.
Yeah, no, that's a good plan. Normally, I do it the other way around. When we get a prediction, I can apply some assumptions, like for the charcoal kilns, for example. I know they have a certain size limit, and then I just filter out all detections which are larger than that or not round enough. But it would be good to tell the model in advance that they should have approximately these properties.
Yeah,
integrating some expert knowledge can sometimes be a good idea to sort of lessen the need for large training data sets.
Yeah, that's a good idea. I will look into it.
There's another chat question.
Yeah, I think it is. It's already out in their VMS. I need to double check that with Liselott, but it should be. And if it's not already, then they're just being a bit slow.
So you mentioned the work on sort of trust in these models, and you mentioned also going into sort of developing the model for cultural remains. Do you have some other visions of what you could do in the future?
Oof, I have many ideas. One of the other things that is poorly mapped in Sweden is small ponds in the forest landscape, especially ponds which appear and disappear depending on the season. I haven't had the chance to work with like normal color images before, like aerial photographs or satellite imagery. So that's something I want to investigate a bit. And also this soil moisture map is a static map right now based on vegetation patterns. But if we have, let's say, runoff prognosis from the SMHI, we can make predictions into the future as well, what it's likely going to be the next coming week. Or we can also apply satellite imagery to calibrate the map, to make it more dynamic in the time perspective. So it would expand and contract depending on the season.
Cool. Would those data sources be sort of frequently updated then?
Yeah, that's the question, depending on which path we take. The satellite imagery is updated with a delay of 3 months, so it's not that useful. But if you take the meteorological data from the Swedish Hydrological Institute, for example, SMHI, those are updated every day, and also you have a forecast 10 days into the future. So, and I think they have an open API which we could plug into this, so it shouldn't be that hard.
Sounds cool. Do we have some more questions?
Yes, here. Nice talk, William.
Thank you.
I think you have done a lot of work there. At least what you presented kind of cover a lot of stuff, and you have tried to use, application from different areas, sort of, and then try to put it in for your purpose here for your work. So I was wondering, how was it when you, let's say, when you do transfer learning or any others there? What were the main challenges when you tried to transfer those how things have been used for other domains and for your purpose in this case. I mean, you didn't really touch those things. It seems just work. I'm sure that it was not just, you know, straight away working like that. So if you could give a little bit of, share some of those challenges with us.
I haven't actually done the transfer learning yet. That's something I'm working on right now. But my secret weapon is I'm really good at making mistakes in a rapid fashion. Sometimes I learn from them. Most of the time I don't. But some of the biggest challenges for me has mostly been with my own skills. I'm a soil scientist. I don't have the skills in machine learning or deep learning. So for example, when I started with deep learning, I tried to install TensorFlow on my own, on my computer. But then at SLU, the IT department synced up our user data with other computers. So then I had real issues with my Python environment. It took me a while before I realized I need to use virtual environments and Docker containers. But yeah, I missed some of those skills, which could have been really a time saver.
Yes, of course. Yeah, I understand that. Yes. I guess even okay, maybe not transfer learning, because I suppose it was near the end of your presentation there. Yeah, I was just interested with this, how you could use this data from the moon, you know, those pictures that you inverted like that. I think that was very smart. I mean, very nice to do that. And but I mean, even earlier in your talk, you talk also about you know, like you use this image segmentation and so on. I mean, it's quite common that it's used, of course, in anything related to images. However, for this purpose, the images are not that clear, because you use images that you kind of, how would you call it? That you try to shape from the LiDAR data. It's not real image, kind of.
Yeah.
So I also wonder how that could translate directly there.
Yeah, that's it didn't is the short answer. Normally, I mean, all the tutorials online and most of the examples you come across use these free band RGB images, which have values between 0 and 255.
Exactly.
But with LiDAR data, we have values from like minus something to plus something else, and it's never the same. So they have to be normalized first into something between like 0 and 1 with 32-bit float or something. I mean, you can't feed the raw digital elevation model, because that have values from 0 to like 2000 something, which is the highest mountain in Sweden, and that doesn't work either. So the challenge here is to find ways to filter the digital elevation model into something that makes sense to train on. The high-pass media filter is one, because it just finds the local topography in each of these chips. And the next challenge is to retain the coordinate system as well, so the output image has the same coordinates and projection as the input image. Otherwise, it's quite useless.
Mm-hmm. Okay, so, sounds there are a lot of things there, but thanks.
All right. I think a final thank you to William for this great talk. It was really interesting to see everything you've done. Next seminar, we'll have a bit of a Christmas break now. So next seminar will be 12th of January. So welcome back then. We'll have Mark D. Plumley, who's a professor in Oxford, I think, going to talk about AI for sound. So welcome back then. University of Surrey, sorry.
Thanks for having me.
Thank you.
Thank you.
Bye-bye.
Thank you very much.
Thank you. Bye.